Today's lesson is about similar triangles and slope. Your learning target says, I can determine the relationship between similar triangles and slope. Let's think back. When we learned about similar figures, back in our dilations days, we found that all corresponding angles were equal between the figures and the sides were always in proportion. On a piece of graph paper, I would like you to graph the line that connects the ordered pairs 0, 2, and 8, 14. Now on that same piece of graph paper, you're going to connect 0, 8 to 4, 8 with a dotted line. And on that same piece of graph paper, connect 0, 11 to 6, 11 with a dotted line. So pause me, get all these things graphed, and then come back for checking. All right, so here I have a picture of mine. The diagonal line, that was the first line I had you draw, and then I had you draw the two dotted lines. So I have a smaller triangle. Let's make that green right here, my smaller one. And I have a larger one that looks like this. So there's one placed on top of the other. Would you say the corresponding angles are equivalent? Well, obviously these angles have to be the same because they're one right on top of the other. And this corresponding and this corresponding are equal because they are 90 degrees. And in a triangle, if you have two corresponding sets of angles that are equal, then the last one has to also be equal. So, would you say they are equivalent? I would. I would say they are. And are the sides in proportion? Well, let's look at the little guy. If I'm going from the bottom to the right angle, I would count up 1, 2, 3, 4, 5, 6 up for the green one. And then if I went over, I'd go over 1, 2, 3, 4. So the top to bottom compared to the left and right sides are 6 to 4 on the little guy. Let's see on the big guy. If I counted up, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9 up, and 1, 2, 3, 4, 5, 6 over. And I want to know if these are in proportion. So I could simplify them both. I could cross multiply. I could find a scale factor. I think I'm going to cross multiply. 6 times 6 is 36, and so is 4 times 9. So yes, they are in proportion. So these triangles are similar. All right, so let's find some slopes. Now we know that they are similar to each other. Let's find the slope of the line that corresponds with the hypotenuse. Ooh, that's a big word. That means the side across from the right angle of the small green triangle. Now, if you remembered when I was doing my sides, I counted up. I was actually doing slope for you, but that's a secret. Don't tell anybody. So my change in y over my change in x, I counted up 6 and over 4. In simplest form, up 3 and over 2. That is the slope of the hypotenuse of the small triangle. If I do the same thing for the bigger triangle, the one that I did in, was it red, I think? I also already did that for you. So I counted up 9 and over 6. And if I simplify that, my goodness. So the slope of the hypotenuse of the smaller triangle is exactly the same as the slope of the hypotenuse of the larger triangle. Well, that makes sense because one is laying on top of the other. They have the same steepness. It is actually the same line, just extended. So let's try again. I want you to graph the figure that connects these three ordered pairs, 0, -10, 0, negative 6, and 6, negative 6 with a solid line. And then on the same piece of graph paper, I would like you to draw a second figure that connects the ordered pairs 3, negative 8, 3, negative 2, and 12, negative 2 with a dotted line. So you will have to pause me while you're working on that. Come back when you're ready to check. Okay, let's decide if these triangles are similar. So we actually have two of them. We have this little guy and this bigger guy. All right, the little guy. Would you say the corresponding angles are equivalent? Well, I know one of them in particular because this right angle and this right angle have to be the same. So I would say that I have two parallel lines, parallel, parallel, with a transversal. Oh, we're going back into another unit, which means that this angle and this angle are corresponding, so they're equal to each other. And like I said before, if you have two angles out of three that are corresponding and equal, that makes the last one equal, this one and this one. So yes, corresponding angles are equivalent, sides in proportion. So let's count up. We count up 1, 2, 3, 4, 5. No, I didn't. Let me count that again. 1, 2, 3, 4. 4 up on the little guy, and 1, 2, 3, 4, 5, 6 over. How does it look on the big guy? This goes up 1, 2, 3, 4, 5, 6 going up, and 9 going over. And I want to know if those are proportional. If I use cross products, this is 36, that is 36. They are equal. So these are similar. So if we found the slope of the line that corresponds with the hypotenuse, remember that's the side across from the right angle, of the little green triangle, I counted up 4 and over 6 simplifies to 2/3. If I found the slope of the line that corresponds with the hypotenuse of the larger, or the red one, I went up 6 and over 9. That also simplifies to 2/3. So it appears that the slope of the line for the hypotenuse of the smaller triangle is exactly the same as the slope of the line for the hypotenuse of the larger triangle. So I'm thinking that looking at my diagram, my line is the same line, it's just extended from the smaller one to the bigger one. So of course it makes sense that the slope would be the same. In your interactive math notebook, I want you to write in words what you believe is the connection or the relationship between slope and similar triangles, and explain why your theory makes sense. So pause me here and come back when you're done. So we only looked at right triangles, and so we can only really hypothesize right now about right triangles. But according to what we've seen, the slope of the hypotenuse of two similar right triangles is equal. The slope is going to be equal because the sides are in proportion, which means that the angle or the steepness of the line that connects those two edges has to be the same. Since we are talking about similar triangles, it's a good time to talk a little bit of theory. Now, you're not going to have to remember this, you're not going to have to recreate it, but I like to make sure you understand the math behind how we get some of these formulas rather than just, trusting me that I know what I'm talking about. So, we can use two similar triangles to figure out the origin of our formula y equals mx. That was our direct variation formula. So what I did was I drew a line that passed through the origin and any ordered pair xy. So it went from here to here. So we're talking about this line right here. And this is the hypotenuse of a right triangle. I'm telling you that the triangle is similar to one whose hypotenuse runs from 0, 0 to 1, m. All right, so I have the little blue guy right here. This is my little blue guy. And then I had a larger red guy right here. All right, so if we wanted to find the slope from 0, 0 to xy, we would subtract our y coordinates, y minus 0 on top, x minus 0 on the bottom. That gives me y over x. Similarly, if I want to find the slope from 0, 0 to 1m, I would take m minus 0 and 1 minus 0, which would give me m over 1. And I know those two slopes are the same. So I know y over x is the same as m over 1. Y over x is the slope of the big triangle, and m over 1 is the slope, or the hypotenuse, of the little triangle. Now, if I want to solve for y, I have to get rid of this divided by x business. So if I multiply both sides by x, my x's over here would cancel, and y equals m over 1 times x, or y equals mx. Okay, a little bit of theory for this one as well. Remember, you don't have to recreate this or give it back to me in any manner. I just want you to understand that these equations are not just coming out of thin air. I'm not just making things up, that there's actually some mathematics behind how to get that. And it's based in similar triangles. So we're going to draw a line that passes through the y-intercept of 0b, that's right here. Oops, let me change that color, 0b, and any xy, any coordinate. So we're talking about this line right here, and it is the hypotenuse of both of my similar triangles. So I have a similar triangle. Let me change colors here. I have a little tiny triangle that's right here. Can you see it? And then I have a larger red one that's right there. Okay. So if I want to find the slope from 0b to xy, I would simply subtract. So I am going to take y minus b as my numerator and x minus 0 as my denominator. So that will just simplify to y minus b over x. If I want to find the slope of my little guy, I would still take my y coordinate, y minus y on top, x minus x on the bottom, and that gives me m over 1, because those will cancel, and you can't do anything with that. I know that these two slopes are equal to each other. So the y minus b over x slope, that is for the big triangle, is the same as m over 1 of the little triangle. So these are the slopes. They are the same because they are similar triangles. If I wanted to solve for y, the first thing I would do is I would multiply by x, both sides. That leaves y minus b on one side and m times x, that's a times, on the other. Not quite done. Let me pull it up here. Y minus b on one side, m times x on the other. I would have to add the b to both sides. and that would be y equals m times x plus b. So these formulas that we've been using actually come from the relationship between similar triangles and slope, which simply is that the slope of similar triangles is equal to each other.